Hello and welcome. In this video, I want to take a look at the notion of a surface integral of a scalar function. And I'm going to start by reminding you of what we meant by a line integral of a scalar function, right? So suppose we had a curve C parameterized by r of t, which is the vector x of t, comma y of t, comma z of t. This is in R3, and t is between a and b. And suppose we've got a function f of x, y, z, that is a function of three variables and it's defined on the curve C. Then we say the line integral of f on the curve C is this. We denote it this way, the integral along C, f of x, y, z ds, where ds is a little bit of arc length. When you convert that all into t's, the f of x, y, z is essentially f of r of t, right? So we're taking values of t, calculating x, y, and z, plugging them into f. Then you're multiplying by a little bit of arc length, and the way we calculated that arc length is the length of r prime of t times dt, right? So speed times a little bit of time is a little bit of distance. Now I want to take this idea of that line integral of a scalar function and turn it into a surface integral of a scalar function. So essentially like a double integral, rather than integrating just along a line, we're going to be integrating along or across the whole surface. Okay. So here we go. Suppose you've got S, a parametric surface defined by r of u comma v is x of u comma v comma y of u comma v comma z of u comma v comma, no last comma, just end the vector there. Just get in the groove there, and all of a sudden had to come out of it. So u and v is in some region D in the UV plane, and if you've got f, a function of x, y, and z that's defined on the surface S, then we can talk about the surface integral of the function f on the surface S, and we denote it this way. We make it look like a double integral because it is. You've got two variables, u and v, that you're going to use. So over the whole surface, f of x, y, z d capital S. Okay. Now, pretty much every textbook you're going to read doesn't give this as a definition. They do it as like a Riemann sum. They say the limit, as m and n go to infinity, and they do, essentially they take the surface, they cut it up into a bunch of little pieces, find the area of each piece, multiply it by that height function. Now this is not unlike what we did to do surface area in the previous video, right? Because we subdivided up the surface into a bunch of little parallelograms, and we then added up the area of all those parallelograms. The only difference now is before you add up all those areas of the parallelogram, you multiply it by a height function. You multiply it by f, right? So the surface integral is the height function times ds. That's a little bit of surface area. Okay, and when we convert that into u's and v's, it looks like this. So this is the integral, the double integral over d of f of r of u comma v times, and remember that little surface area element was the length of the cross product of the partial of r with respect to u and the partial of r with respect to v. So you got to find those two partial derivatives of the parametric function, and then cross them, take the length of that, and then you're going to multiply it by du dv or dv du, depending on which order you want to integrate. Okay. Now let's do an example, and this example is a simplified example of a question that my brother-in-law called and asked me one time. My brother-in-law is an engineer, and well, I got lots of brothers-in-laws, but one of them is an engineer. And he said, I need to calculate the center of gravity of this part that we're making. It's a pipe fitting. And so he had circular pipe that then was being transitioned into rectangular pipe. And so they had this, circular opening on one end, it's a rectangle open on the other, and it's somehow tapered from one to the other. And he said, I need to be able to find the surface area. Not the surface area, I need to be able to find the center of mass. Now, this isn't a solid thing, right? It's a pipe. It's got to allow, I think it was gas that was going through it, but So I'm not just doing a triple integral like we did earlier. I need to do this just on the surface because that's where the material is. It's only on the surface of this pipe fitting. I remember asking him, though, what do you need to know the center of mass for? I picture a little pipe fitting. He says, well, we need to know where to put the little ears on it, or put the ears on it so that we can attach it to the crane and pick it up. How big is this thing? He said, well, it's for a nuclear power plant and it's taking the exhaust from the power plant station into the cooling tower. So, the round circle part is, 8 to 10 feet in diameter. It's like, okay, I see why you need a crane. Okay. And I can see why they want to, know where that center of gravity is so that they know how it's going to behave when you pick it up, how it's going to hang and where that center of gravity is. So this is not the pipe fitting, but I'm just doing a center of mass of this surface to show you what type of integral would have to be. Okay, so it's an example of a surface integral of a scalar function at the same time as being an application. Okay. So the thing is, I've got this cone. This is the same cone that we did the surface area of in the previous video. So here's the parameterization. R of u comma v is u cos v comma u sine v comma u, with u between 0 and 1 and v between 0 and 2 pi. I'm going to assume that this thing is uniformly dense. So it's, if you think of it as metal, it's a thin sheet of metal that's the same thickness all the way around. And I want to know where the center of mass of this thing is. Now, I think you could tell by symmetry that the x-coordinate and the y-coordinate in the center of mass are going to be 0. This is symmetric about the z-axis here. So it's really only the z-axis that I need to do. And to calculate z bar, it's going to be the surface integral of the function z ds divided by the surface integral of the function 1 ds. Now, that denominator is just the area, right? But I'm going to, well, there's a lot of ways I think of this. I think this is the average z value. I'm taking an integral of z and then dividing by the integral of 1, so I'm getting the average value of z. Right? But this integral in the numerator is a surface integral because the z is being multiplied by d capital S. It's unfortunate that I'm using S for the name of the surface and d capital S for saying this is surface area. Anyway, but well, both of these are surface integrals of scalar functions. The bottom one is just scalar function 1, and the top one is z. So in the previous videos, we calculated a bunch of things. We see that r sub u is cos v comma sine v comma 1. R sub v, that should say r sub v. Let's make it say. All right, now it says it. So we calculated that. We took the cross product and we took the length and found that the length of that cross product was u times the square root of 2. We then calculated the area. This is all in a previous video. You can go back and watch that video if you haven't already. And the area was pi times the square root of 2. So now I just need to calculate the numerator, which is the surface integral of the function z ds. And so z, where's my parameterization? Z is just u, right? The z coordinate here is just u. So that gets replaced by this u. The length of the cross product of Ru and Rv is u times the square root of 2, then du dv, where u is going from 0 to 1 and v is going from 0 to 2 pi. I can do this separately because it's a rectangular region and it's a product of u's and v's. So the integral from 0 to 2 pi of dv is just 2 pi, and the integral of u squared times, I lost the square root of 2 in there. Hang on a minute. There it is. That square root of 2 is this one right here. Plug in the 1, plug in the 0, subtract. I get 2 radical 2 over 3 times pi. So the average z value is this divided by the area, which is 2/3. So you think about that cone, it was between z equals 0 and z equals 1. and the center of gravity was at 0, 0, 2/3. So 2/3 of the way up. Now, just to compare, I want to do this again, find the z bar if the cone was a solid, right? So think back when we were doing triple integrals, application of triple integrals, we would do the triple integral over the cone of z dv divided by the triple integral over the cone of 1 dv. Okay. Well, the triple integral of the cone of 1 dv is just the volume of the cone, which is 1/3 the area of the base times the height. The base is circle of radius 1, so it's got area pi, and the height is 1, so the area there, that denominator, is just 1/3 pi. The numerator, I'm integrating z dv, and I'm going to do it in cylindrical coordinates. So it's r dz dr d theta. That's what the dv is. And setting up that triple integral, I've got theta from 0 to 2 pi, I've got r from 0 to 1, and then z goes from r up to 1. So remember, look at the cone. Any value of r out here, z starts at the lowest value, which is equal to r, and then it goes up to 1 from there. So anyway, you can do that integral. It's 1/4 times pi, and so 1/4 times pi divided by 1/3 times pi is 3/4. 3/4, notice, is bigger than 2/3. So as a solid cone with a point at the bottom here, that the center of gravity is up at 4/3, but as just an edge, just the surface, the center of gravity is at 2/3. And this makes sense to me because if you think about where the material is, when it's just the surface, as you go up higher, you're getting more stuff because they're bigger and bigger circles. But the circumference of that circle grows as it's 2 pi times r. So it's a linear function of r. So as you go up higher, it's only getting big in a linear fashion. But the area of a circle is pi r squared. So as you're going up, the amount of stuff at each level is going up like a quadratic function. So there's more stuff up high, and so you would expect the center of gravity to be higher. So indeed, that's what happens. As a solid, the center of gravity is up at 3/4, but as a surface, no top, this didn't have a top on it, the center of gravity is at 2/3. Okay, so there's the notion of a surface integral of a scalar function. You got to realize that you're taking that function and you're multiplying it by d capital S. That is a small amount of surface area, which involves that length of the cross product of RU and RV. Anyway, try some of these. They're fun. Enjoy.